please.
So let's start. So we recall just that we have worked and we have understood the complexity of the fast Fourier transform, so FFT, when n is a power of 2. In this case, the complexity is 3/2 n log 2n minus n/2 operations. Then, using this, we have proved that the computation with circulants, again with the constraint that n is a power of 2, it is 9/2n log 2n plus on, both for solution of linear system and matrix vector product. Notice that essentially this complexity is 3 times the complexity of this, just because we have seen that 3 FFT are necessary for making this kind of computation with circulants. So if you have a linear system of size n, and n is a power of 2, or you make a matrix vector product, using this fast algorithm, you obtain this kind of complexity. Okay. Today we make some strange thing. So tablets matrix vector product, and we will prove that the complexity is 18 n log 2n plus on. So going a bit worse than with the circulants, but the interesting fact is that n is generic. Okay, so we start for a special n power of 2, special n power of 2. Here we arrive to a computation. The cost is higher, but n is generic. So if you have a huge n, which is just a prime number, or in general not a power of 2, then the cost is still n log n, and essentially you use a fast Fourier transform with this special size. And this is a kind of interesting. Then the other arrow that we see is that using this kind of algorithm for the matrix vector product with tablets, we arrive to have an FFT with the cost of 18 n log 2n plus on for n generic. So it is fun that using this, we can come back to this, and this, of course, has consequences on computation with the circulants. And generic. So it is a strange dependency graph. We start with something with the spatial size. Here we make the jump to generic, and then using this, you go back to FFT. Okay, so this is the plan for the beginning of this lecture. Is it clear? So this we have done. This we have done. We need to prove this. So we take a generic templates matrix of size n. Okay, and remember here I don't put constraint on the size. The idea is to embed such a template matrix as a principal leading submatrix of a larger circulant. And since we want to apply the matrix vector product with this spatial dimension, the embedding is such that of a larger circulant whose size is a power of 2. So this is the idea, okay? So I write the templates T0, T1 till Tn minus 1, here T minus 1 till T1 1 minus n, here T0, T1, T minus 1. This is our T, okay? Then what we have? We have that in order to embed this in a larger circulant, we need that if here there is a T minus 1, then since the second column is a shift of the first, then here you should find T minus 1. Okay? Then, since here there is T minus 2, at the end, that is here, you should find T minus 2. So it means that here, since it is the circulant is a subclass of templates, also here there is T minus 2. Okay? And you go back till T1 minus n. So this is a spatial circulant and then everything is set because a circulant matrix is just defined by the first column. Then all the rest is a shift. Okay, so you understand that it is uniquely determined at this point. There are no uncertainty. The problem is that this matrix has a size which makes us completely unhappy because the size is the length of this original vector, which is n, plus the length of this vector, which is the first row, excluding the first term, which is n minus 1. So this matrix has size 2n minus 1. And this number is odd. So for sure cannot be a power of 2. So problem, the size of the circulant is odd. That is 2n minus 1. It cannot be a power of 2. So somehow with this enlargement, embedding, for sure we have that the first property is okay. So the given templates matrix is a leading principal submatrix of a larger circulant. But the larger circulant has not the required property of having size of being a power of 2. So this solution is not good, but we are close to the real solution. So let's go. So again, t0, t minus 1, till t1 minus n, t1 till tn minus 1, t0, t1, tn minus 1, tn minus 1, and this is our t. Then here we put zeros instead of starting with t1 minus n, and then we go with t1 minus n till t minus 2 till t minus 1. Okay, so there is the presence of some zero. So here is Cm, and for sure we have to take m larger, strictly larger of 2n minus 1 in such a way that is at least even, but we want a power of 2. Take into account that this is the constant. Is the constant because if the size is less than 2n minus 1, you cannot have the circulant that embed this t. You see that these numbers are necessary. Okay? So it should be larger than 2n minus 1, strictly larger. Then, by cases, if n is already a power of 2, then we take m, the size, equal to 2 times n, which is larger of 2n minus 1, which is the constraint. So everything is nice. It means that the number of zeros you have here is just 1 zero, only 1 zero. The bad case, so this is the best case. The worst case is when n is 2 to the power s plus 1. Okay? So it's like when you have a discretization of a differential equation on a line and you choose 1025 points instead of 1024. Then this creates a problem. Because now, if you take the double will be less than 2n minus 1. Okay? So notice m equal to 2 to s plus 1 is not okay because 2 to the s plus 1, it is equal to times n, which is this. Notice that 2 times n is 2 to the power s plus 1, because there is this 2, plus 2. So 2 to the s plus 1 is 2n minus 2, which is below 2n minus 1. So it's not okay. You cannot put all the data you need. So you have to go to the other power. M equal to 2 to the power s plus 2, which is 4n. But then if you make 4n, there is plus 4, so minus 4. This is the relation between the minimal power of 2, which is larger of 2n minus 1, and this is exactly equal to 4n minus 4. And this is the worst case. You have understood the reasoning? It's very algorithmic in this case. It's not pure mathematician stuff. Okay? So engineers and computer scientists should be quite happy. You have seen the point. So this is the worst case. In the worst case, when you start from a number which is power of 2 plus 1, you need almost 4 times the size, almost there is this minus 4, in order to fulfill the two requirements. that T is a principal leading submatrix of Cm, and at the same time, M is a power of 2, okay? And now we go with the complexity. So, which is the complexity? When you multiply a circulant whose size is a power of 2, this is the complexity, okay? So, if I make Cm times y, the complexity is bounded. I say bounded because this is the worst case of 9/2. Then the size is m log 2m plus om. And now we have to see which is the m. The m is bounded by 4n. Okay, so bounded 4 times n. So here is the 4, 18 n log n plus O of n. This is the cost of multiplying a circulant by a vector. But you don't want the circulant by a vector. You want the taplis times a vector. So now, how to recover the taplis times a vector? By this. So I go slow because it's good that you understand. So we want to compute T times X, X belonging to Cm, generic vector. Then we consider the vector Y belonging to Cm and depending on X constructed in this way. On the top, there is X, and then there are zeros until the size M. Then if you compute Cm times this epsilon of X, because of the zeros here, T multiplies X, T goes on X, and all this part, which is in principle dense, goes on the zeros. So in this product, you have that on top, you have T of X, the first n components. And then here there is something that you are not interested, okay? But the computation of Cm times y of X costs at most 18 n log 2n plus on, and from Cmyx extracting the first n components, you recover T of X as it is written here. So there is an increase of the cost just because your matrix is larger than the original one. And in the worst case, this M is bounded by 4 times the original N. So the 9/2 n log n, since the size is 4 times, 4 times 9 divided by 2 is exactly 18. Still a reasonable number, okay? You have got the point? Is it clear or not?
Yes.
Yes? Okay, so we are here. Now From here, the magical thing of recovering the FFT with this cost when n is generic. Okay? So it is strange that we are using the FFT for the circulants for the tablets, but here there is a logical jump. Here the size are strictly of a certain time. Here it's generic because we're using an embedding algorithm. And from this now we recover the FFT with n generic, okay? And then everything is okay. It means that when you have the FFT with n generic, you can deal with circulants with the low cost, even when the size is not of a wonderful type, because there are specialized FFT for n power of 2, but also for n power of 3 or n powers of n of any prime number. But we don't need this forest of algorithm, because using the tablets vector product in a fast way, that is this, we recover the generic FFT. So we don't need all this forest of spatial algorithms, okay?
Can I just ask a quick question?
Sure.
And are the properties like inversibility of the Toeplitz matrix, do they
Sorry?
lead to, if the Toeplitz matrix is invertible, does this guarantee that the circulant matrix is also invertible?
I've not understood. If the Toeplitz matrix,
if the Toeplitz matrix is invertible, does this guarantee that the circulant matrix is also invertible?
no, there are no guarantee, but in this case, you don't need invertibility because you are using a matrix vector product. So invertibility is not an issue.
Okay.
And your question again is interesting, because when you have a Toeplitz matrix associated with differential equations, for instance, the discrete Laplacian, if you embed in the circulant, then the circulant is singular, even if the Toeplitz is invertible. So there is no spatial relation between the invertibility of the two objects. But in this case, for the algorithmic proposal, you need only the fast matrix vector product. So you don't need invertibility. So at the point so relating with the rest of the course we have done with Maya, I'm talking of the matrix vector product. So if you use a GMRS where the Toeplitz matrix, where the coefficient matrix is Toeplitz, ask yourself which is the cost of multiplying a Toeplitz by a vector, which should be done in GMRS and should be done in conjugate graded. Then the cost is not n squared as expected, but is n log n. Okay? So it's like talking about the cost per iteration.
Okay, so there's no direct solver that can be obtained in m log n using this?
No, the direct solver is for circulants, but not for Toeplitz.
Okay.
For circulants, there is a direct solver, we have seen. Because you can compute in 3/2 n log n the eigenvalues. You check if any eigenvalue is different from 0, and then there is the algorithm for solving the linear system. But if it is circulant, not Toeplitz. You see, here I've written only Toeplitz matrix vector product. I've not written Toeplitz linear system solution, as I've written here with circulants. With circulants, this is true, but for Toeplitz is not. We can guarantee that with Toeplitz, the iterative solvers have a cost per iteration which is n log n. Then if you arrive to prove that the number of iteration is constant, then also the solver in the iterative sense, it is n log n.
Okay. Thank you.
You are very welcome. So now, how to have a fast Fourier transform from a fast Toeplitz vector product for a generic size n. So we are trying to answer to the last question, because then when we have this, then of course with the circulants you can do everything in n log n once you have the FFT. Okay. Now observation. Take X, let's call preliminary observation. Take X square matrix, D1 diagonal matrix, D2 diagonal matrix. If you multiply D1 times X and you ask which is the JK component, since the diagonal is on the left, you are scaling the row. So this is D1 JJ times XJK. You understand? You are scaling the row. If I'm doing the scaling on the right, then this is DKK2 times XJK, because I'm scaling the columns. Okay? Or I can put this in this size, but this, since these are numbers, I can put it wherever I like. Okay? Oh, this preliminary observation is the solution. Okay? Why? Take the scaled Fourier matrix n generic. So we remember which is the expression e to the minus I 2 pi j k divided n j and k from 0 to n minus 1. Okay? Now I have to jump to another, but you remember this. I will write again indeed. So F9 321. So square root of n Fn equal to e to the minus I 2 pi j k over n j and k from 0 to n minus 1. I decide to see this in this way. E to the minus I 2 pi divided n multiplied jk. So I see this, the pi I put here and the 2 I put inside. Okay? No trick, no cheating. Then I use something which is deep mathematics. And of course, I'm joking that 2st is equal to s. I put here plus and here minus. And I'm very terrible. So the deep mathematics is this. Minus 2st is equal to s minus t square minus s square minus t square. So this is equal to what? It is equal to e to the minus I, plus I pi over n. Then instead of this, I write j minus k square minus j square minus k square. And this, of course, identity. Which is equal, in the light of the preliminary observation, notice this index is only j, only row index. And this index is only k index. So this row and these columns, so this is equal to diagonal for j going from 0 to n minus 1 of e to the minus, I have to make the multiplication, 1 pi over n j square. Then this matrix e to the I pi over n j minus k square times diagonal k from 0 to n minus 1 e to the minus I pi over n k square. I've used the preliminary observation. Because if you take this, it can be written as e to the minus I pi of j squared times this times this. And since this depends only on j, then it is a diagonal scaling on the left. Since this depends only on k, it is a diagonal scaling on the right. So if you call this D, is a diagonal matrix, and here is the same diagonal matrix, and this matrix depends only on the shift. So this is a Teplitz. So the Fourier matrix can be factorized as diagonal Teplitz diagonal. So the cost of Fn times x is 2n, that is the cost of multiplying diagonal matrices times a vector, plus the cost of t times a vector. And this cost, as we have seen here, was 18 n log n plus on. But here you add only 2n, so the generic FFT is 18 n n log 2n plus still on, because it was on plus 2n. In conclusion, can be computed as y1 equal to dx y2, and call this y, equal to t y1, y3 equal d y2, y equal square root of n times y3 within 18 n log 2n plus on operations. So at the beginning, we have used the FFT with special size for diagonalizing circulants, solving linear system with circulants, multiplying matrix vector with circulants, and then also for Teplitz matrix vector with generic n. Now we go back at the generic fast Fourier transform can be obtained obtained using templates. So we invert the situation. Okay. And I find this kind of trick quite nice from, okay, an aesthetical viewpoint. I don't know how to say. Okay. Now we analyze more in detail templates structures from a spectral point of view with the idea of having tools for analyzing the performance of given preconditioners. So the first part was essentially on the matrix vector product. Now we go on the spectral properties in order to study the convergence speed of the preconditioned GMRS or preconditioned conjugate gradient. But in any case, you need some information, spectral information on your objects. Okay, so we this is the second part somehow. Okay. Given f belonging to L1 minus 1, 1, we have defined Tn of f like A0, A0, A1, A1, An minus 1, A minus 1, A minus 1, A1 minus n, with Aj Fourier coefficient And since the class of function is quite large, it is interesting to discover that almost all the templates structure you find in application can be interpreted as templates matrices generated by a function. So this helps a lot. Okay. We will show a lot of relationships between the spectral properties of TNF and F itself, which is called the generating function. Okay. Fact 1, F real valued. Since we are in L1, I should be precise mathematically, but there is no problem. Almost everywhere so up to 0 measure set, which does not count in the computation of the Fourier coefficient, since there is an integral. If f is complex valued on a 0 measure set, this does not affect the computation of Aj. Okay. So f real valued almost everywhere, then A minus aj conjugate, it is equal to 1/2 integral minus pi pi f of theta e to the minus j theta. I've written aj, the theta, and then I have to make the conjugate. Now, the conjugate of a product is the product of the conjugate. And when you make the conjugate in an integral, you can make the integral of the conjugate, just because the integral is just a summation. So this is equal 1 to pi integral minus pi pi f of theta conjugate e to the I j theta, the theta. But f is real valued, so if you make conjugate, it remains what it is. Because f is real valued, it remains what it is. And this, by definition, is a minus j, because if you put instead of j minus j, you obtain exactly this. So f real valued implies that aj conjugate is equal to a minus j for every j, which implies that TNF is Hermitian. So f real valued implies that TNF is Hermitian. So implies that the eigenvalues of TNF are real. Real valued, real eigenvalues. Okay, you can see the first relation between the function and the spectrum. Okay. So f real valued almost everywhere implies lambda j of TNF belonging to R because TNF Hermitian. Oh, sorry, it is 11 o'clock, so we stop here and we continue in the second hour to see more relation between F and the matrices. Okay?
Now. Ready.
Usually I should accept probably, okay. This time there is nothing that I should accept, so I can continue. So I start, Maya? You are the master.
Yes, please.
So tell me, I start? Okay, thank you. Okay, so f real valued almost everywhere, all the eigenvalues independently of n, so for any n, are real just because Tn of f is Hermitian. But there is more. If f is non-negative, then Tn of f is non-negative definite. And in fact, if the essential supremum of f is positive, then Tn of f is positive definite. This claim looks a bit of too mathematical. Let's think to f just continues. I'm telling that if the maximum of f is positive, then Tn of f is positive definite. Which means another thing, that the only case where the matrix is not positive definite is the case where f is identically 0. So if f is identically 0, of course, all the Fourier coefficients are 0 and the matrix is 0. But if the function f is non-negative, but the essential supremum, in the continuous case, the maximum is positive, that is, the function is not flat equal to 0, then the matrix is positive definite. There are only two alternatives, identically 0 or positive definite. Okay, which is kind of strong. So if your function is 0 on a big interval and there is just a spike at a certain point, then the matrix is positive definite for any n. Okay, and this is already powerful because by an analytical property of the function that you can analyze very easily, you obtain properties on mysterious objects which are the eigenvalues. Okay, how to prove this? So f not larger or equal to 0 almost everywhere, of course, means that Tn of f is Hermitian. Because we have seen before that if it is real valued, then it is Hermitian. This is a special case of being real valued. So for sure it is Hermitian. Now you should remember what is a positive or non-negative definite matrix. So a positive definite if and only if for any x, x I don't like, for any v vector different from 0 of Cn, v star AB is positive. So we go to this original definition in terms of the quadratic form. If I divide by v star v, is called the Rayleigh quotient, which is very important for analyzing many things with iterative solvers. Okay, you remember this definition. Now I go to check the basic definition. Okay, so I consider v star Tnf v, okay, with v different from 0 of Cn. And I want to prove that this quantity is strictly positive. Or it is equal to 0 when f is identical to 0. Okay? Let's go. When you have a V star matrix V, what is this object? Is the sum for all j and k going from 0 to n minus 1. Okay, usually the vectors go from 1 to n, but in the magical world of Fourier, circulant, and whatever, going from 0 is more useful. So there will be Vj conjugate, then Tnf in position jk, and then vk. This is not special for tablets. This is true if here I put a matrix A, then ajk is a general formula. Okay? Basic things concerning products between matrix and vectors. Okay? So this is equal to what? Sum jk from 0 to n minus 1, vj conjugate. What it is this? This is the Fourier coefficient aj minus k position f of f vk. Why this? Because the matrix is shift invariant. So the position jk depends just from the difference j minus k. Tablets or shift invariant is the same thing. Okay, notice that the word shift invariant is used especially from people working in image restoration, and you understand also the sense shift invariant. So it means that the blurring does not depend on the particular position, is uniform. Okay. Okay, so we have this. Then we go j and k from 0 to n minus 1. Vj conjugate, Vk, and then the j minus k Fourier coefficient. So I'm stupid, I just replace the expression of the Fourier coefficient, and instead of j, I put j minus k because this is written here. So 1 to pi integral minus pi f of theta e to the minus I j minus k, because it's the j minus k Fourier coefficient, theta d theta. Until now is fog, and I understand, but in few moments, the fog will disappear. So 1 to pi integral minus pi sum j and k from 0 to n minus 1 bj conjugate bk. I've put the integral outside. I can do integral summation commute, huh? When the summation is finite. Otherwise, if it is a series, you should talk about convergence, but not in this case because it's just finite. And then there is what? E to the minus I j theta, I prefer to separate, times e to the I k theta, f of theta d theta. So you see that f pj conjugate goes with this, which only has j, and there is the minus, and bk goes with this. We are close to make a miracle occurring, you see? So repeat what it is. L so V star TNF V is equal to what? 1 to pi integral minus pi. Now I separate the summation from 0 to n minus 1 Pj conjugate e to the minus I j theta, because this does not depend on k. I can separate sum k from 0 to n minus 1 bk e to the I k theta f of theta of the theta. Now, if I call Pb of theta this beautiful trigonometric polynomial, okay, which is this quadratic form is nothing else than the integral minus pi. This is Pb theta, the polynomial, and this is the conjugate. And you should know that a number times the conjugate is the modulus square. And now, as a miracle, you see that if f is non-negative, of course, this is non-negative. And again, the fundamental theorem of algebra, this stupid object is a polynomial. So it can have at most a finite number of zeros. So if f of theta is the maximum which is positive, this integral should be positive, because this can vanish only in a set of zero measure, that is in at most n minus one points. Okay, so you see that this quantity, V star TNF V, with V different from 0 of Cn, is strictly positive if S sub of F positive and F non-negative, and V star TNF V is equal to 0 if and only if F non-negative and F identically equal to 0. So if you put the assumption outside that F is non-negative, this can be 0 only when F is identically 0, otherwise it's strictly positive definite. The matrix TNF, because this Rayleigh quotient is strictly positive. Okay? And one should ask why there is so much enthusiasm. Because the information that stems from this are a lot. For instance, localization result. So f in L1 minus pi, small r is essential infimum of f, and capital R is essential supremum of f. Then A, if small r is equal to big R, then the function is identically equal to this constant, and the Fourier coefficient of the constant R such that A0, the first Fourier coefficient, is equal to the constant and all the rest is equal to 0. So TNF is trivially R times the identity, and lambda J of TNF, of course, is equal to R for any J for any N. B, if we are not in the stupid case, because this is really stupid, so the infimum is less than the supremum, then for any n, for any j, lambda j of T and F stay in the open set, small r, big R. Okay? Here a proof. Case A is trivial. If F coincide with the small r, then Aj of R is equal to R for j equals 0 and 0 otherwise, which is equivalent to say that TNF is equal to R times the identity. Then there is nothing to prove. B. If small r is less than capital R. Then we consider TNF minus small r. So f is the function, small r is the essential input. So f minus r is non-negative almost everywhere. Then TNF minus r is positive definite. Which is equivalent to say that lambda j of Tn of f minus r are strictly positive. Okay? For any j from 1 to n, for any n. Do you agree with this? It is what we have seen before. If the function is non-negative with essential supremum positive, then TNF is positive. But if small r is the essential infimum and I subtract to f the small r, then the essential supremum is capital R minus r, which is positive. So the function is not identical with 0, and Tn of f minus r is positive definite. Okay? But Tn of f minus r is nothing else than Tn of f minus r times the identity. Compute the Fourier coefficient of this. All the Fourier coefficient with j different from 0 are the Fourier coefficient of f. The only difference is in the 0 Fourier coefficient where there is the number r. So it will be A0 of f minus r. And if these eigenvalues, if this is the expression, then lambda j of Tn of f minus r are equal to lambda j of Tn of f minus r. So if these eigenvalues are positive, it means that these are positive, that is lambda j of Tn of f is larger than r. And so another miracle occurs. If the function is localized in an interval, then the eigenvalues are localized in the same interval. But for the function, the extreme can be included, while for the eigenvalues are not included. The order is the same. You should consider Tn of capital R minus small f. And then for the same reason, capital R minus small f is non-negative with positive essential supremum, so the eigenvalues are positive, and by the same reason, lambda j of Tnf are bounded by capital R. Now I show you just an example, because otherwise too much theory, you go in difficulty. So take, for instance, this has something to do. So this Tn is a uniform discretization, uniform node discretization by finite differences of the fourth derivative. And you should add like on 0, 1, and you should add this kind of constraint. Uj of 0 equal uj of 1 equal to, sorry, of j of 1 equal to 0 for j from 0 to 1. Okay, so 4 boundary conditions. You obtain this object. Now let's go to analyze this. If you use the Gershgorian circle, you do not obtain anything about positive definiteness of this matrix. But this is a matrix where the A0 is equal to 6, the one on the diagonal. A1 equal to A minus 1, it is equal to minus 4. A2 equal to A minus 2, it is equal to 1, and all the rest is 0. So your f of theta is 6 plus, minus 4 e to the I theta for this, minus 4 to the minus I theta for this, plus e to the I 2I theta, A2, plus e to the minus 2I theta for this A minus 2. Remember that the coefficients on the diagonal you should interpret as the Fourier coefficient. So you reconstruct the function. Which is equal bit of trigonometry 6 minus 8 cosine of theta, the I part disappear, plus 2 times cosine of 2 theta. And more trigonometry, I jump this thing because it's just algebra. This is 2 minus 2 cosine of theta to the power 2. Are we happy or not? Sure. Minimum of f is equal to 0. Maximum of f is equal to 4 to the power 2, 16. Then Tnf is eigenvalues in 0, 16. And so you know that is positive definite, which is highly non-trivial. It is not easy to prove in another way. But if you have, for instance, Tn of theta square times h of theta, you know the Fourier coefficient and you discover that the generating function is this, with h of theta in L infinity, h of theta between 1 and 3, then automatically you know that the lambda j, so this is another example, lambda j of this Tn of theta square h of theta are between, so the minimum is 0 and the maximum is pi square times 3, at most this. So belong to 0, 3 times pi square. And also in this case, by other tools, it is almost impossible to analyze the spectrum. So the fact that TNF obey to the sign of F, it is kind of very important. Okay. Okay, this was M and this is N. Sorry. Okay. And now again a bit of theory. Suppose that you have a vector space with a partial ordering. So not for every pair, but you can tell when something, in some case, when something is smaller than another thing. And B, vector space with a partial ordering. Of course, these two vector space can be different, so also the partial ordering can be different. So if you have phi from A to B such that phi is linear and phi is positive, that is f larger than 0 implies phi of f larger than 0. Of course, this is the 0 of the vector space A, and this is the 0 of the vector space B. Okay? In this case, so this is a definition. In this case, we say that phi is linear and positive. And is indicated in this sense, phi LPO, linear positive operator. Okay? So this is a general definition. According to what we have proven, Tn from L1 minus pi pi. So you have a function in L1 and you go in the space of matrices of size n. According to what we have proven, this operator is LPO. Because if f is real valued and non-negative, then Tn of f is Hermitian non-negative definite. So there is an ordering in the space of Hermitian matrices, and I say that a matrix is larger than the 0 matrix if it is a non-negative definite. Okay? So Tn maps non-negative functions into non-negative definite matrices. Example from the space of functions. Consider like space A, C01, so continuous functions, and as B the same space, okay? And consider this object Bn of f of theta is defined, f of t is defined as the sum for k going from 0 to n of n over k, f of k over n, x to the k, 1 minus x to the n minus k. So if you look, of course, Bn is linear. Since x to the k in 0, 1 and 1 minus x to the n minus k in 0, 1 are non-negative, this is a positive coefficient. If f is non-negative, then of course Pn of f is non-negative. Okay? And is linear with respect to the argument. So is linear and positive. Someone of you knows this object? These are the Bernstein polynomials. So Tn is LPO, Bn is LPO, and there are many other of these objects. Now I want to give you a theorem regarding this space C01, which is a very special theorem. And then we will see, but without proof, because it becomes very complicated, the matrix version. So how to approximate a Toeplitz matrix using circulants, and how to approximate Toeplitz matrix using other matrix algebras. And the key is this theory of linear positive operators. These Korovkin theorems are a huge amount of them in a lot of spaces, but we will see just them in the space of the continuous function on a given interval. And the interval is 0, 1, so a very special situation. But you will understand why this is a very special result. So you have phi n, a sequence of linear positive operators from C01 into C01. So as our Bernstein polynomials, the Bernstein polynomials are just an example. Take a continuous function, you make a sampling, a uniform sampling, and using this uniform sampling, you construct a polynomial of degree at most n. So given a function, you give a polynomial. So you can see them as an operator from the continuous function in 0, 1 into the continuous function in 0, 1. And of course, is linear and positive because, as I said before, in 0, 1, this is a non-negative polynomial. This is a non-negative polynomial. So the product is a non-negative polynomial. N over k is a positive object. So when f is non-negative, it is clear that this combination of non-negative objects is a non-negative object. Okay. Now, here is a more general situation. So Phi n could be your Bernstein polynomial or could be another thing. Okay. Now consider special function g and assume that the infinity norm of this difference goes to 0 as n tends to infinity. But g is not in a large set of functions. G can be 1, g can be the function t, g can be the function t squared. So I'm telling that take the Bernstein polynomial to give a concrete example on 1 and assume that the Bernstein polynomial on 1 converges to 1. So the infinity norm goes to 0. Take the Bernstein polynomial on t, subtract x, and assume that it goes to 0. Take the Bernstein polynomial on t squared, subtract by x squared, and assume that it goes to 0. You understand the point? Is having a approximation of three stupid objects, 1, t, and t squared. Okay? If this is true, then for any f belonging to the continuous function in 0, 1, which could be also nowhere differentiable, so general continuous function, you have that phi n of f of t in x minus f of x tends to 0 as n tends to infinity. Before we go on, I want that you think on the sense of this theorem. You have a way of a process for approximating a function. If I prove that this process is successful on three stupid functions, which do not need to be approximate, so 1, t, and t squared, then this is true for any continuous function in 0, 1. No way how regular it is. Okay, and in the afternoon we will see how this can be applied in the case of sequence of matrices, Taperet's matrices, approximated by spatial circulant polynomials. So now, since there is no time for giving the proof, I think that I will stop here and I will take maybe 10 minutes more in the afternoon, okay? Because otherwise the proof is split and this is not good. It's never good to have something like this. Maya, do you agree?
Sure.
Okay.
Maybe we let the students see if there are some questions.
Sure.
So you may wonder how all this stuff is related to preconditioning and iterative methods, but it comes at the very end.
Yes. I hope to be convincing in showing the link.